This section we're going to look at Euler's method for solving differential equations as well as review separable differential equations. So this is Euler's method, and Euler's method is saying that if we have some function for the derivative, so y prime is equal to some function of x and y, and we're given a starting point, we can go through an iterative process to approximate what the solution to that differential equation is going to be. And we start out by taking steps by h on the x value. For smaller values of x, we get better approximations for our graph. So we start with some x0 value and we add on h to get the next x value, and then we add h to that to get the next x value. And we're taking little steps along the way. To get the corresponding y values, we take the previous y and add on our step times the function evaluated at the previous point. And going through an example will help see this process. So our derivative is equal to x minus y. We know that y passes through the point 0, 1, and we're going to use a step size of 0.1. So x1, we're going to do 0 plus 0.1, or 0.1. Our second x value will be 0.1 plus 0.1, or 0.2. And we're just increasing for each step by 0.1 from that initial starting value of 0. And we could keep making infinitely many x points to use and plot for our graph. I'll stop at 5. Now we need to find out what the corresponding y pair is going to be for each one of these. Y sub 1, on the previous slide it said that we take the previous y value, or 1, plus the h value, plus our step size, times our function, x minus y, evaluated at that previous point. So x minus y would be 0 minus 1. Now we evaluate this, and we get 0.9. For y2, we take the previous y value, this is where the iteration is happening, plus the step size, times the function evaluated at the previous point. So our x minus y is going to be 0.1 minus 0.9. And we crunch these numbers, we get 0.82. Y sub 3. We take the previous y value and we add on the step size times the function evaluated at the previous point. Our function being x minus y, we do 0.2 minus 0.82. And the stuff in parentheses here is completely dependent on what this rule is for our derivative. That's what's going into each one of these parentheses. And we're using the previous point in that function. And this one's equal to 0.758. And then we can do y sub 4. We're taking the previous y value plus our step times our function, 0.3 minus 0.758, and that equals 0.712. And then we can do a fifth point. And we can keep going on and on and on like this, getting an approximation for our differential equation, but the further we go, the further off from the actual graph we're going to be. But we can do a fifth step here. We're going to take the previous value, 712, plus 0.1 times the difference in the x and the y, 0.4 minus 0.712. And that's plugging into that rule again. And this would be equal to 0.681. Now to see what this really is, we can plot these points, and I'm going to jump to my graphing calculator to look at this. I can go into edit one of my lists, and I can put in my x and y points, or you could graph this by hand on paper. But the x values go into list 1, the y values go into list 2, and then I can make a scatter plot. So I want plot 1 on. This first type is the scatter. My x's are in list 1, my y's are in list 2, and I'm going to have boxes on my graph. And I can't really see what's going on if I look at the standard window. I'm going to change this, looking at the numbers that I had for my graph. I'm going to have my x's go from negative 0.5 to 2, which is way overkill, but that's okay. And my y's, I'm going to go from 0 to 2. And you can see a curve starting to take place here. That is an approximation of the differential equation y prime equals x minus y. To get the actual equation for it, y equals this, we would have to do some integration techniques, some differential equation techniques to find it. Some equations we can find exactly, others we have to use this rough, crude approximation for. But that's the thing to remember with Euler's method, is it's giving us a crude approximation for a differential equation. Previous in the year, we looked at separable differential equations, where we have a function for the derivative that involves x and y. And we're going to review that today also. For these problems, y prime, remember, that's dy dx. This is equal to 2x over y. We want to separate the x's and the y's. So I'm going to multiply both sides by y and multiply both sides by dx. I get y dy equals 2x dx, and now that it's separated, I'm going to integrate both sides. Integral of y with respect to y is 1/2 y squared. The integral of 2x with respect to x is x squared, and one of these two I need to put a plus c on. Now to find out what the original equation was, we solve for y. So I'm going to multiply everything by 2. And then square root. And I end up with the original differential equation being y equals plus or minus square root 2x squared plus 2c. So it's 2x squared plus a constant. We don't know what that constant is because we don't have any initial conditions set on this. with this problem, you could either solve it for y if we wanted to look at a graph, or leaving it in this form down here would be okay. There's a variety of different ways we could write this. We could just write it as y squared minus 2x squared equals some constant. But any of these are acceptable for the differential equation solution. I want you to try this one before watching the rest of this video. Try to go through the separation with this, then we'll come back and deal with these initial conditions. So go ahead and pause the video right now, try to do this integration, and then restart it once you think you're done. Alright, let's see how we did. In this one thing to notice is that y prime is dy dt equals k times y. Doing our separation, we get dy over y equals k dt. We get the natural log of absolute value y equals kt. We can change this into exponential form. Y equals, I forgot my plus c, e to the kt plus c. Or in general, y equals some constant, call it a, call it q, call it whatever you want, but that's what e to the c is, times e to the kt. Now we're given some initial conditions. When t is 0, y is equal to 2. And I'm going to go and plug that in to any one of these steps. If I plug in t equals 0 and y equals 2, we end up getting 2 equals a e to the k times 0. Well, anything to the 0 power is 1, so we're able to find out that a is 2. So our differential equation has become y equals 2 e to the kt. We still don't know what k is, but we can use the other initial condition and say 4 equals 2e to the kt. 2 equals e to the kt, natural log 2. I should be putting in 2 for t. So natural log of 2 equals 2k. So k is approximately 0.3466. Now we know the exact form of our equation. Y equals 2e to the 0.3446 times t. This basic form up here that we started with is the basic form for exponential growth and decay. And this down here would be an exponential growth problem because the rate at which things are growing is positive. And we could use this model now to find out the amount of this substance after 3 days, or after a year, or after any period of time. We could find out what our population is. For instance, When time is 0, the population is 2. After 2 minutes, the population is 4. We can use our model to go beyond that and find other populations at other times. Here's the assignment. There's some problems from 6.1, which are all Euler's method problems. And then 6.3, I'm giving you 3 separable differential equations to practice with, because we're going to use those in the next several sections.